how the MOSFET can operate as a linear amplifier. But what it means is that uh, so far we have talked about or we have analyzed the DC circuits of MOSFETs. Now you see with the gate we have a sinusoidal input voltage Vi, which is time varying voltage. Let's assume that Vi is a sinusoidal voltage, which is consisting of a single tone, and this is superimposed over a DC source VGSQ. So what happens is that you have a the characteristic load line, and wherever this load line intersects with the IV characteristics, we call that the Q point. Okay. Now we have talked about this before as well in detail. So just a quick review of how you get this load line is that you just look at the circuit. Okay. So at the output you have this parameter VDS, and then you have the drain to source current, right? So if we talk of DC quantities only, then applying the KVL at the output loop of MOSFET, you have VDD, you have the voltage drop at ID at the resistor RD. So this is VDD minus IDRD is equal to V naught, which is the output voltage, or you can say this is V naught is equal to VDS. Okay, so these are all DC quantities. VDS. Now notice then when this VDS becomes equal to VDD, then your current is zero. Okay, so when VDS is equal to VDD, the current ID is zero. The current ID is zero over here. Okay, so that's one point on the IV graph. Then the other point is where VDS is zero. So where VDS is zero implies a point where ID is VDD by RD. So it is VDD by RD. Now once you have these 2 points, you just connect those, form a straight line. Okay, and then for a given VGSQ, which is the quiescent, or which is the point at which you will have the Q point. Okay, for example, this is the VGSQ supply, this is the DC supply at the gate. So for this this variable of VGS, once you start VDS, you start with the non-sat region, which is the ohmic region, and then once you are passed beyond the VDS sat, which is given by the overdrive voltage. Okay, this is VGS minus the threshold voltage. Threshold voltage for a given transistor is constant. Okay, given the other parameters like temperature or the bulk effects are not taken into the consideration. So this is pretty much the constant. So VTN is constant. So, but you see, if you go on increasing this DC VGSQ, your Q point is shifting, right? Which means the VDS sat is going to shift towards right. So as you go on increasing VGS, the drain current is increasing. That can explain from the physics or the construction of the device. But from this equation, you see that the VDS sat, which is given by these circles, the intersection of this dotted line and these solid black lines are the transition points from non-sat. This is your non-sat region, and then you have the saturation region. This is non-sat or the ohmic region, non-saturation region. And then you have your saturation region over here, which does not depend on VDS. Okay, so as you go on increasing VDS beyond saturation, the ID is pretty much constant. It does not depend on VDS. Okay, so what happens is that as you increase on, you go on increasing VGS, your drain current is increasing and the Q point is shifting towards right. Okay, I mean this VGS increases, VDS sat also increases. So you are on each VGS curve, the Q point is shifting towards right. Okay, so so once you have your VGS, which is set by the DC source at the gate of the MOSFET, then you apply a certain signal, an AC signal, which is alternating. It's a sinusoid having a certain frequency, and then this VGS is a superposition. This gate voltage is small v and capital subscript GS. Okay, so if we call this V capital subscript GS is equal to VGSQ, which is my DC voltage. Okay, DC voltage at the gate, which on which the transistor is biased. The Q point exists. Then in addition, we have an AC signal. Okay, so previously we have not talked about this AC signal. Now we have, and you will see that due to this AC signal, you will have an alternating ID, or the drain to source current. Okay, so now your VGSQ, which is constant, has the component Vi, okay, which is going to shift your Q point up and down, right? Because VGS has an alternating component, an AC component Vi, which is time varying. So VGS is basically it's over a certain DC on an average value, it is alternating. Okay, it is an alternating, and in return, what it does is it produces an alternating ID. Okay, so you can see with time, you have an alternating drain to source current. Okay, over an average, or say a constant IDQ, which is the DC current. Okay, and then this DC current is mapped to an output. So this DC current, you see over here, you have this like this, then over this, or like this. Okay, then if the output is your VDS, this will be an alternating voltage as well. Okay, so over a certain VDSQ, which is an average or a constant, you will have a sinusoidal output. Okay, sinusoidal output, which is linear. Okay, which is a linear reproduction of the input voltage, right? By linear amplifier, it means you don't have any harmonics. The frequency of the input voltage and the frequency of the output voltage, VDS. Okay, VDS has a Q component, a quiescent component, DC component, and then a small signal component which is varying with time. This is an AC component. Okay, AC component and a DC component, just like current has that, and just like your gate voltage has that. So you linearly reproduce an output. Okay, so this I is mapped onto, from these curves, it's mapped onto the output voltage VDS. So you see this swing is determined by the Q point. So as you see, what happens is, in a linear reproduction of the input signal, first of all, this output is just a scale version of the input. Okay, so you might want to say that Vi multiplied by some gain. I can say that this gain is let's say the gain is a constant K, and then this reproduces an AC signal of the output. Okay, or call it VDS. Okay, so in a sense, it doesn't reproduce any harmonic components. Okay, or you don't have a sinusoid which has a different frequency from the Vi. It's just the scaled version of the input. So it's a linear amplifier. Okay, it's a linear amplifier. What happens if it's a non-linear amplifier? Okay, you see, you can reduce a non-linearity if you have a Q point somewhere over here. Okay, if you have a Q point over here, then what happens is that you might have a swing. So let's say it like this. Then you might have, for example, a negative swing, but the positive swing is going to be cut off, because at this point VDD you cannot go beyond. So this point is supposed the transistor turns off. Okay, so then an output signal which looks like something like this will have an undesirable frequency components which are originally not contained in the input signal. So this might contain harmonics. So the first thing is, you need to bias your transistor in saturation region. You cannot bias it in a cutoff. This is cutoff. Okay, this region is cutoff. You don't need to bias your Q point near the cutoff, or you don't need to bias the Q point in the ohmic or in the non-sat region. To operate the MOSFET as a linear amplifier, it has to be biased in the saturation region. Okay, so in order to have an output which is a linear reproduction of the input, the transistor has to be biased in saturation point. So now figure 1 shows an NMOS common source circuit, the time varying voltage source in series with a DC source. So now we have a time varying source with a DC source. So we assume the time varying input signal is a sinusoidal signal, okay, which is shown over here, sinusoidal signal. Then figure 2 shows the transistor characteristics. Okay, so we have seen We have discussed the DC load line over here. This solid pink line is your DC load line, and the point where it intersects with the IV curves, we call that the Q point. Okay, so this is the DC load line. DC load line. So DC load line is completely determined by the drain voltage, the DC drain voltage VDD, and the resistor RD. Okay, that determines the value of the current ID. Okay, the DC currents, the DC load line is all the quantities, the current and voltages are DC quantities. Okay, similarly VDD is where the current is zero, so DC current is zero. So we have the DC load line on figure 2. We have the Q point, that's where the DC load line, the Q point are the functions of VGS, VDD, RD, and the transistor parameters. So for the output voltage to be a linear function of the input voltage, the transistor must be biased in the saturation region. Okay, so you must understand this, because if the Q point is going to shift somewhere, if you want to bias this in the cutoff region, then you cannot reproduce the input signal. Okay, you cannot reproduce a scaled version of the input signal, so you cannot operate the transistor as a linear amplifier. To operate this as a linear amplifier, the Q point should neither be in the cutoff, neither should it be in the non-sat region, should be somewhere in the saturation region. Okay, and the other thing at figure 2, what figure 2 tells us is the common source transistor characteristics, the DC load line, the sinusoidal variation in the gate to source voltage, drain currents, and drain source voltages. It also tells us the limits of swing that can be obtained. Okay, that can be obtained as a function of so how much your Q point is shifting. You see over here why the Q point is shifting. First, let's understand that. You see, you have an input signal with the DC that is varying with time. Okay, this is over VGSQ, right? This, what it does is it has an AC part, it has a DC part. Okay, then this produces an alternating component of the current ID, which does alternates over IDQ with time. Okay, and then you can map this. Okay, the Q point is going to shift upwards from here and downwards like this. So what happens is that when the Q point is going to shift upward, you will have low VDS, low V out. This is V out. VDS is V out. Okay. So towards the left, okay, towards the left, VDS or V out is decreasing, but the current is increasing. So you see this over here at this point, the current is maximum, but at this point when the Q point shifts, the VDS is minimum, right? So when the Q point shifts towards left, you see what happens is that the Q point is shifting in this process. In the linear amplification of an input signal, the Q point is shifting over the load line. It has to. Okay, why? Because your VGS is not constant. Your VGS is varying on this DC load line like this. Okay, it is varying like this. So this thing maps your current to the output voltage. That is a linear function of the input voltage. That means that the input voltage Vi is linearly amplified by the transistor. So the Q point is shifting. So when the Q point shifts upwards or towards left on VDS scale, the output voltage decreases, but the current is at the maximum. The current is at the maximum. The drain current is at the maximum. On the other hand, when the Q point shifts towards minimum, which determines the limits of this, so the shifts of Q point determine the limits of the maximum output, and this is V naught max, right? This is V naught max, and then you have your V naught minimum over here. Sorry, it's the other way around. This is V naught max, and I've labeled it wrongly. This should be V naught max minimum. This is minimum, and it's the other way around. So when the current is maximum, you have V naught minimum, and when the Q point shifts towards right, then the V naught is maximum, and your current is minimum. Okay, so due to this shift in Q point, first of all, you have determined the limits of the swing, of the output swing that you can produce. And if the transistor is not biased near the cutoff or near the non-sat regions, or in the non-sat or in the cutoff regions, you can produce a scaled version, or you can operate the transistor as a linear amplifier. Okay. All right. So, so again, we have this figure over here. Let's talk about the description. So it's also shown in the figure 2 are the sinusoidal variations in the gate source voltage. Okay, so we have seen that the gate source voltage is also varying. The gate source voltage is varying, which means that the Q point is shifting up and down. The Q point shifts up where the voltage, output voltage reduces, then it shifts down. The voltage or output voltage increases, okay, with time. So then you have also the alternating drain current, okay, which is shown over here. Then you have a drain to source voltage, which is the output. So this is the drain source voltage, which is my output. Then as a result of this all is due to this input Vi, which is over here. Okay, so at the gate you have an alternating signal which is producing an alternating component of the drain current, and then due to the alternate component of the drain current, you have an alternating output voltage. Okay, so you have a DC output voltage, and then you have an alternating DC. You have an alternating AC component of the drain source voltage. Okay, which is the linear amplification of Vi. So this is all due to this sinusoidal time varying input voltage Vi. Now the total gate to source voltage is the sum of VGSQ and Vi. So as Vi increases, the instantaneous value of VGS increases and the bias point moves up on the load line. Okay, so you see this Vi is varying with time, right? So as Vi is increasing, it goes up like this. Your Q point shifts. Your Q point shifts. Your Q point shifts, and it then in turn where this current is maximum, because as VGS increases, the current increases, the drain current increases. Due to that, the output voltage decreases. And then when this Q point shifts downwards, like this, downwards, then the output voltage is increased, because since the gate source voltage is decreased, the Q point is shifted towards right. Your current decreases. Your current decreases. Okay, so you can see it either way. So as Vi increases, the instantaneous value of VGS increases, and the bias point moves up the load line. Similarly, a larger value of VGS means larger drain current. So once you have a larger value of, so you see as you increase VGS over here, you have a larger value of the current ID. Okay, this is the ID axis. And a smaller value of VDS. Okay, so if this is large, then VDS is small. So for a negative portion of the sine wave, the instantaneous value of VGS decreases below the quiescent point, and the bias point moves down the load line. So once the bias point moves down the load line, then your VDS is increasing. Okay, so VDS is increasing. So a smaller VGS means you're coming down this side. A smaller VGS means a smaller drain current. We have a smaller drain current, but the increase with the increased value of VDS, so VDS increasing this direction. Okay. Now, once the Q point is established, we can develop a mathematical model for the sinusoidal or small signal variations in the gate source voltage, drain source voltage, and the drain current. Okay, so all we have to do is we have to see. Okay, we have to see that first of all, we have to establish the fact that ID is given by. We are the drain current that we have in the MOSFET is saturated current. Okay, so in order to have this MOSFET to operate as a linear amplifier, the drain current has to be the saturated drain current. Okay, it has to be in saturation, independent of VDS, right? So it's given by VGS, as we talked about earlier. The relationship in the saturation region is given by VGS minus V threshold. That's the overdrive voltage whole square. So basically, this ID has a quadratic relationship with VGS, which has two components. Okay, you can write this as VI plus VGSQ. Therefore, if you substitute this voltage into your VGS over here, you will find out that this drain current can be bifurcated into the DC current and into an AC component of the current, which is due to VI. Okay, so we can develop a small signal model for that as well. So the time varying signal VI in figure 1 generates a time varying component of the gate to source voltage. So in figure 1, this Vi is at the gate source voltage. We are talking about Vi means the input voltage, okay, the input voltage at the gate, which is AC. So in figure 1, the time varying signal source Vi in figure 1 generates a time varying component of the gate source voltage. So in this case, VGS is Vi. So if you throughout this discussion, you will be noting that there is a difference in notation. The notation for this small signal AC quantities is that you have a lowercase subscripts. This lowercase subscript, this is a lowercase subscript. It denotes AC quantities. Okay. Similarly, you have lowercase letters V, which denotes the voltages. So these are AC voltages. Okay. But if we talk of DC quantities, then if I have a DC current, then it will be capital I, capital uppercase subscript D, which denotes the drain current. If I have to write the drain current for AC, it will be I small d. Okay, this is AC. So AC is lowercase, DC is uppercase. So where VGS is the time varying component of the gate to source voltage. Now for a field effect transistor to operate as a linear amplifier, transistor must be biased in the saturation region. This is important. Okay, you must remember this. For field effect transistors to operate as a linear amplifier, the Q point, or the intersection of the load line and the IV characteristics, it should happen in the saturation region. It has to be biased in the saturation region. So and the instantaneous drain current and the drain to source voltage must also be confined to the saturation region. So you don't want to move the Q, because Q is moving. You see, in the linear amplification process, the Q is moving. The Q is moving in this region, and this region is still saturation region. It's nowhere near to the cutoff. This is the cutoff region where the transistor turns off. Cutoff means the ID is 0, so you don't want to move the transistor into cutoff. Okay. And similarly, you don't want to have the Q point near the non-sat region. Over here, you might also have, you can't have a linear reproduction of the input signal near the cutoff or in the ohmic or in the linear regions. Okay, it will produce a voltage like this in either regions like this. So you don't want this voltage. Okay. Now, when a symmetrical sinusoidal signal are applied to the input of the amplifier, symmetrical sinusoidal signals are generated at the output as long as the amplifier operation remains linear. Okay, so this is important. So for linearity, the rotation has to be in the saturation region. So we can use the load line to determine the maximum output of a symmetrical swing. If the output exceeds this limit, the portion of the output signal will be clipped and the signal distortion will occur. So this is what I have tried to explain before. For example, if it is near cutoff, then this upper limit is going to be clipped. Okay, which was not the case in the if the Q point is in the saturation region. You can determine the maximum output swing, and it's not clipped, so the frequency content stays the same. You can say that VDS is just a scale version of the input voltage, but over here, well, this is something else. This is not, VDS is not equal to KVI because it contains harmonic content. Okay. So in case of field effect amplifiers, the output signal must avoid the cutoff ID equal to 0 region and must stay in the saturation region. That is, VDS should be greater than VDS sat. So this maximum range of output signal can be determined from the load line. Now you see the load line is going to give you an idea in the transistor in saturation region what is the maximum swing you can have. Okay, when the Q point is shifting up and down. Okay, so before we develop a small signal model, let's talk about some transistor parameters and the notation. So notations used for the time varying as well as DC current voltages in this discussion are summarized in the following table. Now, as I explained previously, for DC values, we're going to have uppercase I and V. Okay, since we're going to talk current and voltages, the drain current and output voltages, or the gate source voltages. So everything is uppercase. Okay, I is uppercase, V is uppercase, subscripts are uppercase. For instantaneous AC values, AC components, everything is lowercase. Okay, I, V are lowercase, subscripts are lowercase. However, the total instantaneous values will have, total instantaneous values means, okay, it means that the VGS is consisting of, it's a total value, so it will consist of a DC value, VGSQ, which is the DC source at the gate. Okay, and then it has a small time varying AC signal with it, which is VGS or VI. Okay, same thing. So is this is the instantaneous value. Okay, and this is instantaneous value because it has a DC value to it as well. Okay, and on the DC value you have a riding AC signal, right? So it's like this. You have a VGSQ, and then on that you have the maximum and minimum of small VGS variations, and it continues. Okay, so it's like this, maximum, minimum. So this is total instantaneous values consisting of both the DC and AC quantities. But the difference between this DC and AC quantities, it has a DC and AC component, is that, so I'm writing AC is small because the subscript and the notation is as such that the subscripts are lower and I and V cases are the letters are also lowercase letters. But in instantaneous values, uh, the subscripts are uppercase. So subscripts are uppercase, then you must remember that this is an instantaneous value consisting of both the DC and AC components. Okay, then later on we're going to talk of phasor values. To differentiate these phasor values, this is the reverse of total instantaneous value over here. You have the small case subscript. Okay, over here you have the large scale subscript. You have small case subscripts, but you have large or uppercase I and V letters. Okay, so these are phasor values. We're going to use them later just to differentiate between the notations. And notations are well defined, and they're quite meaningful in their own respects. Okay, so now from figure 1, let's use these notations in describing the small signal model. Let's keep the fact that in mind that small letters and small subscript denote AC values, large letters, large subscript denote DC values. So let's proceed. Figure 1 is, if you recall, we have seen an NMOS transistor over here. We are interested in the small signal operation of this device. So first of all, your total instantaneous gate source voltage is the DC plus the AC. Okay, and we have said that this VI can be replaced by small v and small subscript GS, which is an AC quantity. So this is DC quantity, this is AC quantity. Okay, now where VGSQ is the DC component, VGS is the AC component. The instantaneous drain current, which is for the saturation region, the IV characteristics are written as such. Now this VGS has both the AC and DC components. Okay, so let's substitute this over here in this equation. Kn is the conduction parameter of transistor. Vtn stays the same. Okay, you don't need to, if you're not considering any temperature change effects or any sub-threshold conduction, etc., or a body effects of the transistor, Vtn is constant. Okay, you can treat this as a DC quantity. Therefore, V is capital and this lowercase is also capital. This is the DC quantity. Okay, the only AC quantity that exists is inside this VGS, and then you will see that this is inside ID as well. Now, substitution of VGS into ID yields. So if you substitute that, you can expand this into DC and AC quantities. Okay, so let's keep the DC quantities together over here, and then you have this AC quantity. If you expand this quadratic equation, the first term totally consists of all the DC quantities. Okay, the second term has the DC quantity and the AC VGS. Then the last term is purely AC. Okay, it's a square of VGS. The VGS is the AC quantity. Now, this equation, okay, I have moved this equation over here. So let's continue from here. The first term on the above equation is a DC or a quiescent current IDQ. Now this I have defined previously is a total DC quantity. So let's call this IDQ. That is my DC drain current. Okay. The second term is a time varying drain current component that is linearly related to the signal VGS. So this is a time varying DC current. Okay, I can write this as ID. Okay, you can see that these terms are existing over here, right? So we have this term over here, we have this term over here, right? But this term is over here. What about the third term? Well, the problem with the third term is that now you see the third term is proportional to the square of the signal voltage. You see, if so, what we considered before was that this input voltage, small signal input voltage, which is VGS, AC quantity, is a sinusoidal as a sinusoidal nature. That is, it consists of a certain frequency, call it sine of omega naught t. Okay. Uh, Amplitude is not important, but what happens if you square this? When you square this, then you're asking for harmonics, right? I mean, sine square omega t, if you recall the identity, cosine twice omega naught t is 1 minus twice sine square omega naught t. Okay, which means that you can express your sine square term in terms of cosine 2 omega naught t. Okay, so basically this is 1 minus cosine twice omega naught t. You can express it like this, all divided by 2. So this is in fact my sine square omega naught t. So this is my VGS square as well, right? I mean, this is how we define this. So this is my VGS squared. Okay. Now what happens is that if we are going to consider this third term into instantaneous value of the drain current, well, it's going to produce harmonics. The harmonic is twice of the fundamental frequency, and it's going to produce a DC term as well, which is undesired. Okay, and it's going to interfere with this DC term. So how we can remove this? Well, all we need to do is to assume small signal conditions. The small signal conditions are that your VGS, the amplitude, the magnitude of VGS is much less than the DC term, the DC IDQ term. It's not IDQ, but less than, you see over here we have a time varying signal due to VGS, which is being multiplied by twice VGS Q VTN. So that's the DC part. So for a sinusoidal input signal, the square term produces undesirable harmonics. You see over here, this is the second harmonic, or non-linear distortion in the output voltage. So to minimize these harmonics, we require VGS to be much less than 2 VGS Q minus VTN. So if this quantity is much less than this quantity, okay, if this quantity is much less than this quantity, then addition of this quantity to this quantity is not significant. It's not important. So you can remove this term altogether. Okay, we don't need this term, which means that the third term in the drain current equation will be much smaller than the second term. All right. So VGS much less than 2 twice VGS Q minus VTN represents a small signal condition that must be satisfied for linear amplifiers. Otherwise, you don't have a linear amplifier. For linear amplifier, remember that the output voltage, which is VDS, which is AC component of VDS, has to be a linear, has to reproduce your input VGS or VI, has to linearly reproduce the input voltage, except that it is multiplied by some scalar, let's say capital K. So if you consider this third term, well, it's not the case. Then VGS has the harmonics, and it's not the scale version of the input, right? So we have to remove this. In order to remove that, we have to make sure that VGS, the input, the VGS is your input voltage. Its magnitude is much less than VGSQ, which is the DC, where you are going to VGSQ is your defining the Q point at the gate source DC voltage. So the difference of VGSQ minus threshold, whatever this quantity is, the magnitude of VGS has to be much less than this. So the third term has to be negligible compared to the second term in order to satisfy the small signal conditions, and also for the transistor to operate as a linear amplifier. Okay, so neglecting the VGS term, we can rewrite the drain current as follows. Now we have the instantaneous drain current, which consists of IDQ, which is the DC term, and the purely AC term, which is due to this VGS. This is again the DC quantity multiplied by VGS. Okay, You have removed the third term. So this is the small signal condition. This over here is my small signal condition. I can proceed further without this. So let's assume that VGS is much less than twice VGSQ minus VTN. Okay. All right. Now, so again, the small signal implies linearity, so that the total current can be separated into DC component and AC component. The AC component of the drain current is given by as such. So the small signal drain current is related to the small signal gate to source voltage by the transconductance gain G of M. Okay, so transconductance means if you take the ratio of ID over VGS, then you can define a quantity in amps per volts, which is the transconductance gain of the MOSFET. Okay, and that is given by twice Kn VGSQ minus VTN. Note that this transconductance gains not only depend on VGS, but it also depends on the MOSFET conduction parameter. It means that it depends on the width to length ratio of the channel. It also depends on the geometry of the MOSFET. Okay, what it says is that your output drain current, we'll see in the small signal current circuit, is GM, which is a transconductance gain, GM into VGS. Okay, so as you see, the units are in amps per volts. So the output drain current due to the input VGS alternating source, which VGS is the alternating sinusoidal source with time varying source. When it gets multiplied with the transconductance gain, GM, it produces a linear or a linear AC current, ID. Okay, so the ID is in ID is the drain current. Okay, which is produced by the transconductance gain GM and the input voltage VGS, right? So the transconductance is a transfer coefficient relating the output current, this is the output current, to the input voltage, which is VGS, right? And can be thought of as representing the gain of the transistor, right? It's the gain of the transistor. And the other way to obtain this transconductance can also be obtained from the derivative. So if you consider this this instantaneous ID over here, now if you forget about the third term, let's consider this part only. And you take the partial derivative of ID with respect to VGS. Now if you do it like this, partial ID by partial VGS, then you see this, the first term is out. Okay, it's a DC term. For the second term, you're left with this quantity only. So you're left with this quantity only. This is the transconductance gain, right? This is GM. This is GM, and GM is being multiplied by the input voltage, and then the output is the current. Okay, so you can obtain this by the partial derivatives of the instantaneous drain current by VGS under small signal conditions, and that VGS is a constant. VGSQ is a constant, it's a DC quantity, which is again twice Kn VGSQ minus VTN. So this can also be written in terms of the DC current. Okay, remember this IDQ. This IDQ is this term. Okay, so if you take the square root of that, it is VGSQ minus VTN under root of Kn, and over here the way you have written VGS. Sorry, the transconductance is twice Kn VGSQ minus VTN. So you can express this in terms of IDQ. IDQ is this one. Okay, this is your IDQ. This is your IDQ. So if you take the under root, it comes in the square root. Okay, with Kn. So you see IDQ. IDQ is square root of IDQ is equal to square root of Kn multiplied by the difference term, the overdrive voltage VGS minus the threshold voltage VGSQ minus the threshold. Right. Then since this is from IDQ, there's a factor of 2 over here. So this factor of 2 is coming outside over here, right? So this is under root Kn IDQ, under root Kn IDQ. So you can express GM in terms of the DC part of the drain current as twice under K and IDQ. So if for so the advantage of writing in this way is that if you have the DC part of the MOSFET transistor amplifier, you can write the transconductance gain, okay, because this parameter is usually known. This is the conduction parameter of the transistor. So in terms of the DC current, you can write the transconductance gain directly, okay. All right. Now the drain current versus the gate to source voltage for the transistor bias in the saturation region is given in the following equation. It's shown in figure 3. Now this shows that the transistor start conducting after the threshold voltage, and the conduction is quadratic with respect to VGS. It has to be, okay, given this relationship. So the transconductance GM is the slope of the curve if the time varying signal, because this is again, this is an instantaneous current. So with respect to VGS, partial VGS, you have the slope, okay. So this slope is your transconductance gain, GM, in terms of amps per volts. So if the time varying VGS is sufficiently small, the transconductance GM is constant, which means if there is small variation, you take a small part like this, then GM is constant because the slope is constant. It's a linear slope, okay. So with the Q point in the saturation region, the transistor operates as a current source, okay. So the input, because the input GM is the transconductance gain, and the input is VGS, and the output is the current, right? So the transistor becomes a current source. The output is the AC current. I should write it like this. Sorry, this is not the instantaneous, but the subscript is small d. Okay. So when the Q point in saturation, the transistor operates as a current source, and it's being linearly controlled by VGS. This is my VGS. So VGS controls the output current, ID. Now if the Q point moves into the non-sat region, the transistor no longer operates as a linearly controlled current source. Okay, if it moves in the non-sat region, first of all, you are going to have harmonics. It's no longer a linear amplifier. Okay, so you're going to have distortion. Then, as shown in equation, the transconductance is directly proportional to the conduction parameter Kn, which in turn is a function of the width to length ratio. Therefore, increasing the width of the transistor increases the transconductance gain of the transistor. So over here you see there is a dependence of this factor on the transistor parameter conduction parameter Kn. Kn is given by, if you recall, is given by W by L into the parameter that is the electrical parameter Kn prime, which consists of the mobility and the oxide capacitance, okay, divided by 2. Okay, so if you consider the geometry, so the Kn is again dependent on the geometrical parameters of the channel or the MOSFET device, and it's also dependent on the mobility of the charge carriers and the capacitance of the oxide. Okay, so it's also dependent on these parameters. The transconductance gain is dependent on Kn parameters. All right, so figure 3 is the drain current versus gate to source voltage characteristics with superimposed sinusoidal signals, right? So with the changing current over IDQ, you produce a VGS that has an average value VGS, and it's varying with time, right? That's the output. So it's like a current source, like a current. It's the other way around. From the changing VGS like this, we are going to have an alternating drain current. So it's like a current source. Okay, that's described earlier. Now, okay, this is example 4.1 from the course text. It says to calculate the transconductance of an n-channel MOSFET. The parameters are given for an n-channel MOSFET. Threshold voltage is 0.4 volts. The electrical conduction parameter is 100 microamps per volt squares. The W by L ratio is 25. So assume the drain current, DC drain current is given as 0.4. So first thing is you evaluate what is the conduction parameters. So this is Kn prime over 2 W by L. Just substitute those values. Okay, this is given as 100 microamps. So if you can bring it down into milliamps, because you will have this Kn in milliamps per volt squares. So 0.1 100 microamps is 0.1 milliamps per volt square. So 0.1 over 2 into 25. That's a dimensional quantity, W by L. So this is 1.25 milliamps per volt square. Now, assuming the transistor is biased in saturation region, the transconductance gain is determined from the DC drain current. Okay, so you have this GM as twice under root of Kn IDQ, and just take the product and substitute those values. You'll find out that this is 1.41 milliamps per volt. So it means your ID, the uh, output AC drain current, is 1.41 times VGS. Okay, now you can see that this is indeed a linear amplifier because we were considering this transistor to be biased in the saturation region. Therefore, ID is just a linear amplification of, it's like a current source. So for the input is my VGS and the output is my drain current, right? And those are linearly related with a constant GM, 1.41 times. So 1.41 times uh, the input gate source voltage, AC voltage, transforms into a linear AC drain current IT, right? So this is because the transistor is biased in the saturation region. So it's like a current source. The input is my voltage, the output is my current. So the value of the transconductance can be increased by increasing the transistor width to length ratio and also by increasing the quiescent drain current. So you can bias a transistor as such. Your VGSQ, the DC VGSQ could be large, so you can have a large drain current. Okay. Otherwise, the transconductance parameter is also dependent on the physical dimensions of the transistor. Yeah. Okay. All right.